So you're in the right place. We did a little R&D on the title today to be a little less generic than design for 3D printing, but that's essentially what this talk is. I'm going to try to talk today about my top 10 rules for design for print. And these are sort of rules that I have learned both the hard way on my own and also sort of by culling through the Thingiverse universe and trying to learn from other designers at the same time. And I'm going to try to do these 10 rules in 20 minutes or less, and then get some questions from you guys or hear your design tips if I have missed any. So as Laura already said, my name is Kacie Hultgren. I go by the name PrettySmallThings, and this is the kind of work that you might see from me if you logged on to Thingiverse. And let's get started. So our number one rule is the pretty common one that most people hear about, and that is the 45-degree rule. When we're working with desktop 3D printers, and in this talk today, when I say desktop 3D printer or just 3D printer, I mean the extruder style fused filament fabrication machines that you probably see a lot of examples of over in the 3D printer village. That word desktop 3D printing isn't going to work very well for fused filament fabrication as we continue to see machines like the Form 1 and hopefully some laser sintered nylon in the future. But that's what I'm talking about today. So the 45-degree rule, essentially these printers don't print with dissolvable support material. And so in order to keep your prints fast, easy to clean up, whenever possible, you want to avoid support material. And most printers can build out at about 45 degrees. And after that, the results are going to get looking pretty sloppy. And so you either want to keep this in mind as you're designing. There's some really interesting sculptural work out there from some character designers like Andreas and Fantasy Graph, who are doing some really amazing artistic sculptures that are like fully vetted for 3D printers. So it totally can be done. And then your other option is to cut up an existing design, either of somebody else's or of your own, so you can creatively print it without support material. And I just want to show an example here. So this is I call it plating a design. This is an copy derived from the user Masayuki. And essentially, I just made some creative choices because this would require a lot of support material if you printed it all in one go. But you can make some smart decisions, cutting it off at about 45 degrees so you can print the head separately, and cutting the body in half so you can print the legs sticking up in the air. And this allows you to get a really good print in about maybe half the time sometimes, and just a little bit of assembly. So if you if you don't want to cut up a design, another thing you can do is add custom support material, which is instead of relying on the computer's algorithms to add support where it thinks you need it, you can be smarter than the computer and just add a simple cone or a cylinder to just support that one piece out in the air. The thing about these printers is people say, oh, they can't print midair. Well, they can as long as they have something to start on and something to land on. They'll actually create a bridge between those 2 points. And so if you add some cones or cylinders to create those bridges, you can end up with a design that prints quite a bit faster. And so these are 2 designs by the user Off-Center Creations, and I generally like to create geometry that's a little bit bigger on the base so you don't have trouble with adhesion to the build platform. But you can see he's experimenting with a couple different ways on this Snoopy, adding a little cylinder up to the tail, a couple shapes from the arms up to the ears, to get this printed without a lot of support material, and the same on our Mike Wazowski character over there on the side. So rule number 3, ditch the raft. A raft is a layer of plastic that goes down on the build platform as the first part of the print, and it helps with a few things. It can help with adhesion. It helps level out the build surface if your bed's not perfectly level. And it's usually recommended to new users because it takes some of the options for air out. It's a little simpler to use, but it usually takes a lot longer to put down. And if you're in a hurry, not only is it going to take more time to print, but you're actually going to have to clean it up afterwards and pull it away. And so I usually like to stay away from rafts unless I really need them. One of the times you do need rafts is when you're using support material, and if you've gotten rid of the support material, why not get rid of the raft too? So if you need more adhesion, you can add something that's called either mouse ears or helper discs to get that extra stick in the places that you might need it the most. And so this is a screenshot of a mouse-eared rocket fin can by Tony Buser, who was hanging out in the back there before. One of the things that's really hard to get to stick to a build platform are these thin features, like the fins on this rocket. And so by adding just a little disc on the corner, you can make sure that those thin features stay stuck for the entire print and you don't get a failed print. It's really easy to do this in a couple programs. Tinkercad is one that's great because it allows you to import an STL and then just add some simple geometric objects without a lot of fuss. And I think even if you don't have a full CAD program in your tool set, Tinkercad is one that you can pick up without a problem. Okay, so rule number 4. Know your details. This is something that I've really struggled with because I like to work small and I like to work delicate. And it's really important that if you want prints that are gonna like make it every time, that you know what your printer is capable of. And so this is one of the situations where you sort of want to test. People call them towers, essentially like small, skinny details. Your printer has this thing called thread width, and so it's spitting out plastic in a line, and that line is called a thread width or an extrusion width, and it's usually about the width of the diameter of your nozzle, and most 3D printers either have a 0.4 millimeter nozzle or a 0.5 millimeter nozzle. And to make a circle, you need something that is 2 thread widths deep. And so the smallest features that most of these printers can do are 0.8 millimeters to 1 millimeter. And then there's also a fudge factor, depending on how accurate your printer is and how dialed in those retraction settings are. And so before you sit down to design something, you want to know what that threshold is, because you don't want to start an 8-hour print with some little skinny towers at the top and get to hour 7 and realize that you've designed something that's too small. So again, that rule of thumb is the smallest feature you can create is double your thread width plus your fudge factor. And so that's something you want to test. Like I said, and this is something I run into all the time. This is one of my designs over on the right here. This is a wicker sofa, and that's about this tall. And I knew that the size of the wicker was going to be the minimum I can do on my printer, which is about 0.85. And you can see on the back of that sofa, maybe I should have made it 0.95 because there's actually some areas where the extruder was knocking it around, and I was not as successful. And the other place to keep this in mind, and that caption is wrong, that is a font test card by Design, Make, Teach. Text can be really tough at small sizes on a 3D printer. Again, keep that rule of thumb in mind. To make like a letter, you really want to get a thread width of plastic all the way around. And so the strokes of that font need to be 2 thread widths wide. That's either going to be 0.8 millimeters or 1 millimeters if you want to have readable text in your design. So rule 5. Design in your fit tolerance. And this is something that's people don't always talk about this with desktop 3D printers. It's hard. Fit tolerance is hard, and unlike the really high-end machines that are going to create a design that is a perfect representation of what you have in your computer, a desktop, under $3 sort of class of machines isn't going to do that quite as accurately. And so you need to make some plans for if you have parts that you want to fit together or small holes, to make some of those fit parts a little bit bigger so that you don't need to drill them out before you put your pieces together. So again, this is something I do before I start. If I know I'm going to be incorporating either parts that fit together or other materials like dowels or brass rods or hardware, make a test piece with a bunch of different diameters, print them out, and see what fits in so you can put those correct measurements into your project before you start, so you don't end up, what I'm generally trying to do is prevent iterations. We always say that it's good to iterate on a 3D printer. It's even better if you can get it right the second time, or maybe the third time instead of the 10th time. I usually use, as a reference for me, I do a 0.25 millimeter offset if I want a tight fit, and a 0.4 millimeter offset for removable parts, something like maybe a lid that you want to come off over and over. So rule number 6, use shells properly. If you're not familiar with the slicing process in 3D printers, when you're making a design, you decide how many shells you want per layer and what sort of infill you want per layer. And the shells are essentially copies of the perimeter, and that makes like the thick wall thickness. And then the infill is like a honeycomb design in the middle to keep it from collapsing. And usually we use shells to add strength. Usually like 1 is only for a draft print. You're gonna get a little bit of maybe the motion from the infill transferring to the outside, doesn't look as good. 2 shells is good for most prints, but for something that needs to take a lot of stress, you might want to add 3 or 4. And this is a way, if you're slicing something hollow, like a vase, you can control the width of that vase by adding more or fewer shells. That's like one of the fastest prints you can do is a single walled vase, because a printer can just whip around that outside and keep going up without having to stop and do the infill. They can aid in adhesion. Sometimes adding those extra layers will give you a little bit more time to make sure that that layer is like down before building up further in space. But shells can backfire, and this is a good example of one where it has somebody, I think, posted this up on Thingiverse with the title, "What's wrong with this print?" or something generic like that. And for an experienced 3D printer user, they can look at it and spot it right off the bat. The problem is they're slicing with too many shells, and especially in this object that has text and that has wall thicknesses that sort of change along the edge of this shield. By doing that, you're creating these areas that are actually too small to be filled, and you would get a much better print with this object if you only had 1 shell or 1 perimeter and just used infill. So be careful about those shells. Well, we're talking about thread width some more. Number 7 is optimize your walls for thread width. If you have a design that always has a thread width designed in, like maybe a shelled box that you're gonna use as like a gift box, when you get down into these thin walls, you gotta remember that the building blocks for this technology is a single line of plastic. And so if you have a wall thickness that's 0.8 millimeters, that's 2 thread widths. If you have a wall thickness that's 1 millimeter, that's like barely any different. Visually, you really can't see the difference. But instead of just doing a shell around the edge and a shell around the inside, it's also going to do an infill layer for every single layer of the print. And it's probably going to take twice as long. And so if you're looking for speed, one of the things to keep in mind before you get started is like, what is the thread width of my printer? And if I want it printed fast, maybe it's worth designing the walls and skinny features in your prints so they just take advantage of your thread width off the bat. Or maybe a double shell, so you would have 4 thread widths, something that's 4 thread widths thick. So that's rule number 7. Use multiples of your thread width for thin walls. And then number 8, orient for the best resolution. People don't realize that when we're talking about resolution, we're really only talking about Z height. When you hear some things that we can print at 100 microns, and that's the high resolution print, or Ultimaker just announced that their printer can do 20 microns as a high resolution print, we're only talking about Z. I've already been talking about this concept of thread width, and that doesn't change. It's gonna be your nozzle, well, I can't say that equivocally. For most people, like, you're gonna use the same thread width throughout your design, and it's either gonna be 0.4 or 0.5. Now, if you can drive your Z height down to 0.02, 0.02 is like, what, 10, 20 multiples of 0.5? The thread width that it lays down is like a rectangular shape. It's always going to be the same width regardless of how thin you make it. And so depending on how you orient a design, especially something with like sloping parts, it can really make a difference. And let me show you an example. So which is the worst print here? It's pretty obvious, right? The one that sort of has these this upper right-hand corner, that is the one that looks the worst. Would you be surprised to find out that it's exactly the same resolution as the one below it? Obviously, the one below it isn't a stellar print. It's not super high resolution, but the appearance is a lot better. On one, the low resolution print here is a 300 micron print, and the high resolution is a really medium resolution these days, is an 150 micron print. And you can see on this design that, you know, sort of the diagonal one, the lower right-hand corner to the upper left-hand corner, I don't know, to me they're sort of equivalent. But one of them took twice as long. And so it's just, let me just show you sort of an example here. You can see this video, which I hope is running. There we go. Oops. So these prints were printed in two ways. The one that looks really low resolution was printed flat, and because it has these low sloping areas, the resolution looks way worse than the similar print that was printed standing up, because it takes advantage of the fact that we can get much thinner layers in the Z-axis than we can on the X and the Y. So if you're working with artistic prints, or and even prints just with a rake, like something like a ramp, it's really important to choose your orientation wisely. And then we have orient for stress. Prints can delaminate or break along layer lines, and this is particularly true of ABS prints. Some people say like, oh, ABS is really strong. And ABS is really strong compared to PLA, but it also breaks much more than PLA does. PLA tends to hold its layers together better. And so if you have a design that's gonna need to take some stress, you want it to like ease a little bit, like these pin connectors, version 3 by Emmett. This is made to sort of go into a little slot and pop into place. And so if this print could be printed standing up rather than laying down, but Emmett's smartly chosen to orient it so that the stress is along like the long layer lines rather than at a layer height break, because otherwise this design would not be terribly structurally sound. All right, and number 10 sort of cheats, because this is actually 3 tips. So print-in-place designs that you sort of essentially peel off the build platform and they rotate or move or flex. These are sort of, I think, the holy grail for a lot of designers who are sort of starting out with 3D printing, trying to figure out how you tackle these types of prints. And I did a lot of sort of looking through Thingiverse earlier this year, trying to figure out like what are the commonalities that bridge these prints. And one of the rules that I came up with was pull the design elements to the platform. So this umbrella design by Zombo, it's tough to see in this picture, but she's essentially taken like all of the mechanical operations of an umbrella and just being really smart about pulling all of the parts that need separation onto the build platform. Because especially if you're not going to use support material, that's like the best place to separate your parts. And so that's my first tip for tackling the print-in-place designs. The second is to use 45-degree overhangs to either build up or build out. This rotator cuff bracelet, there's a really awesome YouTube video, but essentially it's printed. The red one is how it's printed on the plate, and it has essentially 45-degree sort of helical sweeps that when you lift it up, the bracelet sort of like falls down in these tracks. And the reason that it can be held in place, as we learned earlier, that 45-degree rule, that's the maximum sort of angle you want to have. That's how we get parts that sort of interlock within one another without needing support material. And then on the end, this is one of my chairs. You can sort of see, this is also printed without support material, that I was using some bridges to create the seat between the legs, and then also building out at 45 degrees to make it a little bit bigger, a few more millimeters up. And then another tip is to use bridges for captive parts. That's how the hinge on this print-in-place box is tackled. There's a hole in the middle of each of those hinges, and essentially the bottom of the box and the tops of the box are printed flat on the build platform, and there's some really smartly placed bridges in between those hinges that allow you to pull that box off the platform and close the lid right away. And then the other one is gap print carefully, and this is sort of something that people have have been experimenting with for a while, but like a bearing with sort of an enclosure with balls that rotate around inside. If you leave air in a print, the problem is if you print in midair, your printer will print something. And in this case, printing a ball, if you leave a little bit of a gap before it starts, the plastic underneath is cooled. And so as it's leaving the hot plastic on top, it won't adhere as strongly. And so usually with a little bit of force, you can break it apart. The trouble is that depending on your printer, this is one of those variables that's really wide, and so it's hard to create designs that successfully use this to distribute widely. But it's sort of fun to experiment with. All right, so those are my top 10 rules. This is me and how you can get a hold of me. Twitter, web, Gmail, and I also use this name on Thingiverse. And do I have a couple minutes left? Or are we out? I'll take a couple questions. I know that was really fast. Yeah? This presentation will be on YouTube, right? Later. In a couple months, this presentation will be on YouTube. I haven't distributed it, but maybe I will. Anybody else? No? Yeah. They're totally different. They're totally different. And that's like the reality with all of these different processes is they all have different rules because the material behaves differently. It's an entirely different plastic that's different. This laser-sintered nylon, for example, is really stretchy. You're not going to have problems delaminating. So these won't help you at all. Sorry. Yeah. Hi, Matt.
Hi. So you're giving a lot of advice for things you can extrapolate for design in general.
Yeah.
What are some strategies that you stumbled on for like a that actually maybe is not useful, but helps you really crack something that you're going to go with?
You know, I think my real strategy is that I used to sort of like create a design and then test it until it worked. And now I keep all this in mind before I start. And I do as much testing up front as I can so that once I send it to the printer, I'm pretty confident that it's going to go ahead and print. Because the modeling time is really what's hard. And then if you're not using a parametric modeling program, I tend to use AutoCAD, which unlike like OpenSCAD or Inventor and some of these other ones, it doesn't have as robust parametric capabilities. And so if in my wicker couch design, I need to bulk up all those diameters by 0.2 millimeters, which seems really inconsequential, but could be the make or break for that design, I have to do it all over. And so I really try to figure as much of it out beforehand as I can. And I think that wraps up my time, but I'm gonna be hanging out here answering any questions or talking to you. And I'm also giving an intro talk tonight at 6 and tomorrow at 4, and I'm talking more tomorrow in the afternoon about the work that I do in scale on 3D printers. Thanks for listening.